Well, the energy of an electron and its position are also complementary because the energy of an electron depends on its velocity. If we can't know the position and the velocity, then we can't know the position and the energy. We can know one or the other. So for an electron with a specific energy, the best we can do is describe its position in terms of an orbital. Now, orbital and orbit are very similar words, right? Orbital just has a little AL stuck on the end of it. And so I think a common misconception is that students start to think of orbitals as being the same as orbits. Orbits were in the Bohr model of the atom. We talk about a planet orbiting the sun, and that is the kind of orbit that's in the Bohr model. It's a circular or elliptical pattern and it's predictable. But we've learned from quantum mechanics that we cannot predict the path of an electron. An orbital is a probability distribution map of where the electron is likely to be found. The position of the electron is likely to be within this region, but we can't say exactly where it is. And many of the properties of atoms that we observe are related to the energies of the electrons. So the energy of the electron is actually more significant to know than the position of the electron. So we tend to focus on the energy. This brings us to Schrodinger's equation. Now, we're in kind of a difficult level of understanding here because we're talking about some very complex math that takes a lot of education and study to understand. And so a lot of this is probably not going to make a lot of sense. I don't claim to completely understand this. But hopefully when we get to the end, you'll grasp the big picture, and that's what we're going for. So this is Schrodinger's equation. And Schrodinger's equation has to do with wave functions. Okay, this allows us to calculate the probability of finding an electron that has a particular energy at a particular location in the atom. We can't pinpoint its position, but we can make a probability map. So when we solve this equation, we get wave functions. And the wave functions have the symbol psi, and they're used to describe the wave-like nature of the electron. If we plot psi squared, we get a three-dimensional representation of an orbital. And so when we calculate these things, we find out that the shape, the size, and the orientation in space of this orbital, this region in which the electron is likely to be, are determined by three integer terms in the wave function. So there's three whole numbers in this wave function that determine the region in which the electron can be. And these are necessary to quantize the energy of the electron. We have observed that the energy of electrons is quantized. These are called quantum numbers. So the first three are integers. The fourth one is not an integer. So the principal quantum number has the symbol n. The angular momentum quantum number has the symbol L, not to be confused with a 1. That's an L. And then there's the magnetic quantum number, m sub L. The fourth one is spin, and that's m sub S. I don't necessarily like the letters they chose, but we don't have much choice. We just have to deal with them. So let's talk about each of those quantum numbers. The principal quantum number, n, this determines the overall size and energy of an orbital. This corresponds to Bohr's energy levels. Bohr had energy level 1, 2, 3, right? And 3 had higher energy than 1. N can be any integer that's greater than or equal to 1. 1, 2, 3, 5, 9, Those are possible values of n. The larger n is, the higher the energy of the electron, and the larger the orbital size. We can calculate for hydrogen that the energy in that level n is equal to minus 2.18 times 10 to the minus 8 joules times 1 over n squared. So if n is 2, 2 squared is 4, this would be 1/4 of this number. The energy of an electron is negative because the electron's energy is lowered by its interaction with the nucleus. So compared to an electron that's loose, an electron that is part of an atom has a negative energy. As we go up in these energy levels, principal quantum levels, the difference between the orbitals gets smaller. And that's similar to Bohr's energy levels. So if we represent energy on the y-axis, and this is for hydrogen, for principal quantum number 1, this is the energy of the electron. And for principal quantum number 2, it's up here. It's less negative because as we go farther and farther away, the electron is closer to being loose or free. And what they're saying here is this difference between level 1 and 2 is larger than the difference between 2 and 3. The difference between 3 and 4 is smaller. And as you keep going up, the energy level rises, but the difference gets smaller. And that's because of that 1 over n squared term. The next quantum number is the angular momentum number, L. This is also an integer, and this determines the shape of the orbital. And L can be 0 up to n minus 1. So if you're in principal number 5, then L can go up to 5 minus 1, or 4. So you could have 0, 1, 2, 3, and 4. In principal quantum number 1, you only have one value of L, and that's 0, because 0 is 1 minus 1. The value of L is given a letter designation, and this relates to the shape of the orbital, because this angular momentum quantum number determines the shape. So L equals 0 is given the designation S, 1 is P, 2 is D, 3 is F. Now, does anybody wonder where did they get S, P, D, and F, and why isn't it A, B, C, D? This had to do with the experimental figuring out of all of this. They were looking at emission spectra from different elements. And these describe qualities of the line spectra. And so S, blanking. Hang on. Sharp. I knew that. S is sharp, and P is principal, and D is diffuse, and F is fundamental. I actually looked those up last night because I was always forgetting what F was. Now I've forgotten what. The first one was sharp, principal, diffuse, and fundamental. And then there's the magnetic quantum number. This specifies the orientation of the orbital, the direction in space that the orbital is aligned relative to the other orbitals. Values for this one are from minus L to plus L, including 0. And so this tells us how many orbitals of a particular shape that there are. So if L equals 2, M sub L can go from minus 2 to plus 2. And so we can have minus 2, minus 1, 0, plus 1, and plus 2. So that tells us there are 5 different orbitals with this quantum number L equals 2. 2 is P, the P orbitals. No. 2 is D. 2 is D. It's a lot to get into your head. Then there's the spin quantum number. Electrons have spin. And this is a very simplistic way of thinking of it, but you could think of them as like tops spinning clockwise or counterclockwise. It's not what they're doing, but it's good enough. And so this is a fundamental property of an electron, and they all have the same amount of spin. It's just an orientation. So they call plus 1/2 being an up spin and minus 1/2 being a down spin. So they're opposite of each other, but equal in amount. So how do these numbers describe an orbital? Each orbital has a combination of the first three quantum numbers. So if n equals 1, and L equals 0, and m sub L equals 0, this is what we call the 1s orbital. This 1 is the principal quantum number. S is the letter designation for L equals 0. When S, P, D, F, that's 0, 1, 2, 3 for L. Orbitals that have the same value of n are in the same principal level. And the Bohr model is not correct, but it's much easier to visualize. And so I think of the principal quantum numbers as being like a group of orbitals that are in the same level. So like kind of in the same general orbit, same distance from the electron, from the nucleus, and roughly the same energy. Orbitals that have the same values of n and L are said to be in the same sublevel or subshell. Okay, so this makes it easier to talk about. So for principal quantum number n, there's only one possible value of L. It has to be 0. And for L equals 0, there's only one possible value for m sub L, and that's also 0. So this is the 1s orbital. In the second level, we can have L equals 0 or L equals 1. L equals 0 is an s orbital. And there's only one possible orientation for that, and so there's only one of these orbitals. For L equals 1, we have 3 possibilities for the angular momentum number. -1, 0, and +1. And so there are 3 different orbitals that are designated 2p. The difference between them is just their orientation in space. They have the same amount of energy. They're just arranged differently in space. When we get up to n equals 3, now we have 3 different possibilities for L. L equals 0, that's s, the s orbital. There's only one of those. L equals 1, that's a p orbital, and there's 3 possibilities. And L equals 2, now m sub L can go from -2 up to +2. So there are 5 different d orbitals. And we haven't put the spin of the electrons in there yet. Somebody must have a question. It's either so clear or so unclear, right, that you can't even formulate a question. And I'm guessing it's the latter. That's how I would feel. In general, the number of sublevels within a level is equal to n. Let's go back to this picture. The first level doesn't have, it only has one sublevel, so it's kind of even dumb to talk about a sublevel. N equals 2, the s orbitals form one sublevel, and the p orbitals are another sublevel. And then n equals 3, we have 3 sublevels. The s ones, the p, and the d. And so there's 3 different levels within a level. That's what a sublevel is. The number of orbitals within a sublevel is 2 times L plus 1. I personally don't find that very helpful. The number of orbitals in a level is equal to n squared. I don't find that very helpful either, but there it is. So what do we need to do with stuff like this? Well, let's list the quantum numbers associated with all of the 5D orbitals. Well, 5D, we've got N, L, and M sub L. For 5D, what's the principal quantum number N? It's the 5. This is the principal quantum number. D is what value of L? 0, 1, 2, 3, S, P, D, and F. So for the D orbitals, L equals 2. All 5D orbitals have n equals 5 and L equals 2. What are the possible values of M sub L?
-2, 1, 0, 1, 2.
Yep. From minus L, which is 2, minus 2, we have minus 1, we have 0, and then all the way up to plus 2. There are other values of L available for n equals 5, but we're talking about the 5D. The D specifies what L is. And so the only thing we can look at then are M sub L. So how many 5D orbitals are there? How many values of M sub L are there? 5. So there are 5 5D orbitals. Any questions? Each set of quantum numbers is supposed to specify an orbital. So these sets, A, B, and C, but each set has one quantum number that's not allowed. So we're supposed to figure out which one is not allowed and replace it with one that is allowed. Well, n equals 3. Can you have n equals 3? Sure. If n equals 3, can you have L equals 3? No, because L is 0. L equals 0 to n minus 1. So what's the largest value of L that you can have? 2. So we could replace this with 2. We could replace it with 1 or 0 also. Those are also allowed. Could M sub L, I don't know how these things happen. It's amazing more of these things don't happen. And that's a typo. M sub L, could M sub L equal plus 2 if L equals 2? Yeah. M sub L is from minus L to plus L. So this is an acceptable set of quantum numbers. If we put 1 in here, would that work with M sub L is plus 2? No, it wouldn't. Because if we put 1 here, then M sub L can only go up to plus 1. It can't be plus 2. Let's look at letter B. Well, n equals 2 is fine. Could L equal 1 if n equals 2? Yeah, because L needs to be 0 up to n minus 1. So here, L is n minus 1, so that's okay. If L is 1, can we have M sub L being minus 2? No. What could it be? Could be minus 1. We could also choose 0 or plus 1. Those are also possible values for that. Let's look at C. if n equals 1, can L equal 1? No. If n is 1, L has to be what? 0. If L is 0, can M sub L equal 0? Yeah, in fact, it has to. Because M sub L goes from minus L to plus L. If L is 0, then M sub L goes from minus 0 to plus 0. It is 0. Any questions? Yes?
So on the first one, why can't L be 3 again?
On the first one, why can't L be 3? Because the value of L goes from 0 up to whatever n is minus 1. So for n equals 1, there's one value of L. For n equals 2, there's 2 values of L. For n equals 3, there's 3 values for L. So if you can remember this somehow, then you can do a question like that. Let's look at how this applies to atomic spectroscopy. So we saw the atomic spectra, and they were colored lines, right? Each of those colors is a particular wavelength. The wavelength of light is related to the energy of the light. So each wavelength, each line, corresponds to an electron transition between orbitals. The orbitals have different energies. And when you go from one orbital to another orbital, the energy changes. If an atom absorbs energy, an electron is excited to a higher energy level. But that's not stable. And it eventually comes back down to its original level. And when it does that, it has to release the energy that it absorbed. That energy comes out as a photon of light. I am more accustomed to teaching Chem 3A. I've done it a lot more. And so I have better analogies. And so some of my analogies for them don't work as well for this level of understanding, but I think some of them are still helpful. I think of the electrons as being like teenage boys. I've had a series of teenage boys in my house, and I've got more coming. Got another one becoming a teenager next week. Teenage boys have this natural state, which is flat, horizontal. They want to be laying down most of the time. They're either sleeping or texting or watching TV or something. And occasionally, they'll get this burst of energy, and they'll get up, they'll go to football practice. They'll get up and do something. And then what happens? They go back to their normal resting position. And that's how I think of electrons. They're in an energy level, and if you zap that atom with energy, the electron will absorb that energy, go to a higher level, but it's not going to stay there. Eventually, it's going to come back down. And when it does, the energy that it absorbed has to come back out. Conservation of energy. What goes in has to come back out. So it comes out as a photon of light, and we can measure the frequency of the light and figure out the energy of it. So this is a diagram illustrating this. So if we have an electron in the first principal energy level, and we excite it with energy, maybe it goes up to level n equals 3. Well, it's not going to stay up there forever. It'll go up there, and then it'll start coming back down. And it does not have to jump all the way down. It can jump down to a different level. So here we have it coming from level 3 down to level 2. And it releases energy in the form of electromagnetic radiation. And we can measure the energy of that. The energy of this light corresponds to the difference in the energy levels between those two principal levels in the atom. The electron has to gain the right amount of energy. It's like on the bus, exact fare. They don't give you change. You need the exact fare. But you can't give them extra. And so you have to have just the right amount of energy to bump that electron up to a higher energy state. And that corresponds to the difference in the energy levels. and then they come back down and they release that energy. So the wavelengths of light can be predicted for the hydrogen atom by calculating the difference in energy between any two states. In energy state n, principal quantum number n, there are n-1 energy states it can transition to. So it can generate n-1 lines. Both the Bohr and the quantum mechanical models predict these lines really well for a one-electron system. What element is a one-electron system? Hydrogen. Both models work really well for hydrogen. The Bohr model only works for hydrogen. So the energy of a photon released equals the difference in energy between the two levels. So when you talk about the difference in energy, same pattern, it's the final energy minus the initial energy. And this is going to equal minus 2.18 times 10 to the minus 18th joules times 1 over the final level squared. So this, where's my pen? This should look like that equation for calculating the energy of an electron in hydrogen. So it's the final minus the initial. So here's the initial. Let me fix that up a little bit. And there's the initial. Final minus initial. Well, if you simplify that, you can factor out the minus 2.18 times 10 to the minus 18th. And you've got 1 over the final level squared minus 1 over the initial level squared. And then what we need to remember is that the change in energy for the atom is opposite in sign to the change in energy for the photon. If the energy of the atom goes down, the energy of the photon goes up. And then the other thing to remember is that the wavelength of the light is equal to Planck's constant times the speed of light divided by the energy. And we're going to look at things like this in lab today. And we're going to actually use the wavelength of light that we're going to measure, and we're going to calculate which principal energy levels the electron is transitioning between. So here's a look at the different transitions for hydrogen. So if you excite the electrons in hydrogen, we can observe a transition from n equals 5 to n equals 2. That's as kind of a bluish purple light with a wavelength of 434. And from 4 to 2 gives us sort of a teal color, and from 3 to 2 gives us a red color. These are the three transitions where the wavelength corresponds to visible light. There are other transitions occurring as well, and they are still electromagnetic radiation, but our eyes can't detect them. These transitions fall in the infrared range. These transitions from 5, 4, 3, and 2 all the way down to 1 fall in the ultraviolet. Yes? Pardon me? Yeah. What is that? N equals infinity. That's ionization. So that's removing an electron completely. Yeah. If you zap it with enough energy, you can actually kick the electron out. Good question. So determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So n equals 2 and n equals 7. Which is the initial? 2. From 2 to 7. So 7 is final. And then we need that equation. This guy right here. It's 1 over final squared minus 1 over initial squared. 2.18 times 10 to the minus 18. So delta E minus 2.18 times 10 to the minus 18 joules, 1 over n final squared minus 1 over n initial squared. So final is 7 squared minus the initial is 2 squared. A lot of these problems come down to how well do you communicate with your calculator. So the way I'm going to do this is I'm going to do negative 2.18 EE minus 16 times the quantity 1 divided by 49 minus 1 divided by 4. And then I'm going to close parentheses. And so I'm getting negative, I'm sorry, it's not negative, 5.01 times 10 to the minus 19 joules. Yes, question?
You said it was 16, not...
You mean this number?
Yes.
Let me check. It's 18.
I thought you put it in as 16 to your calculator.
I may have said 16. I'm looking at my calculator, and I did do 18. I do stuff like that all the time, so thank you for asking. Is it reasonable that this is a positive number? The energy absorbed is 5.01 times 10 to the minus 19 joules. Did we answer the question yet? No. What's the question? What's the wavelength? I just started calculating. We needed to calculate that, though, because we calculate the wavelength from the energy. So on one of those previous slides, we saw that wavelength was hc over E. So Planck's constant, 6.63 times 10 to the minus 34 joule seconds. Speed of light, 3.00 times 10 to the 8th meters per second. And the energy that we just calculated, I'm going to throw a couple of sig figs back in there. Oh, come on. There's 1, 2, 3. That'll be good. Times 10 to the minus 19. And that was joules. So check our units. Joules cancel. Seconds cancel. We're left with meters. This is good news. We're going to have a wavelength in meters. 6.63 EE minus 34 times 3 EE 8 divided by 5.005 EE minus 19. That's still just 2 sig figs, though. It's 4.0 times 10 to the minus 7. Oh, my brain. 4.0 times 10 to the minus 7 meters.
Why is it 2 sig figs?
Well, that's a good question. It shouldn't be 2 sig figs. It should be 3. I don't. Yeah, thank you. Because I had it in my head somehow. And I think, that's how we all make mistakes. That's why group effort, 2 heads are better than 1. So let's call that 3.97 times 10 to the minus 7. That's better. Okay, what else did I mess up on? Any questions? So this is the wavelength of light that gets absorbed when an electron moves from n equals 2 to n equals 7. Energy is coming in